In part 2 of this presentation, I want to take a closer look at the vapor compression cycle. On the top right, we can see a schematic of the heat pump with the main components: 1, the compressor; 2, a heat exchanger, the condenser with the secondary fluid on the right, where we can reject heat to; an expansion valve at 3, another heat exchanger, the evaporator, at 4, where again a secondary fluid circulates and we can extract heat. So how does this work? Well, essentially at A, the compressor sucks in a cool gas at low pressure. The compressor increases this pressure, and by increasing the pressure also increases the temperature. So at B, we have a high temperature, high pressure gas that enters the condenser. In the condenser, a phase change occurs from gas to liquid, and during this phase change, a lot of energy is transferred to the secondary fluid, to the hot sink. So at D, we get a high pressure, low temperature fluid that enters the expansion valve at 3. There, the pressure is reduced, and at E, we get a low pressure fluid gas mix that enters the evaporator. In the evaporator, again, a phase change occurs here. The fluid is, let's say, evaporated. Again, a lot of energy is transferred, and we extract energy at a low temperature from the cold source. At A, again, we have a cool, low pressure gas that can enter the compressor, and the cycle is closed. So what we see is that in this cycle, we can harvest heat, we can extract heat at a low temperature, and we can reject it at a high temperature. Hence, we pump heat from low to high temperature. How does this work, and why does this have a high efficiency? So we need to consider a few fundamental relationships. The first one is the gas law, and the gas law basically says that pressure and temperature are related. We can see this on the graph on the top right, where for different gases, R134A, R410A, and R290, refrigerants used in the heat pump system, we can see that there is a relationship between the temperature and the pressure. At absolute zero, the pressure is 0, and at higher pressure, at higher temperature, we get higher pressures, and at higher pressures, we get higher temperatures. And for each gas, the temperature on the right is different, so each gas has its own characteristics. But important here, and we can see that also in the equation, is that if we increase the temperature, the pressure has to increase as well. And the other way around, if we increase the pressure, the temperature has to increase as well. And this is exactly what the compressor in our heat pump does. It increases the pressure, and thereby also it increases the temperature of the gas. The second fundamental principle is the phase change. Like I said, phase change transfers a high amount of energy. If we take a look at water, 530 times more energy is transferred with the phase change than with just a sensible temperature change. Another point is that the temperature at which the phase change occurs does not change. So during the phase change, boiling water remains 100 degrees. There is no temperature change during the change of liquid to vapor. On the other hand, however, there is a relationship, and we can see that in the graph here, between pressure and the temperature at which the phase change occurs. At low temperature, we have at low pressure, the phase change between vapor and liquid occurs at a low temperature, while at a high pressure, the change between liquid and vapor occurs at a high temperature. So this is what is used in the heat pump to transfer the heat from a low temperature to a high temperature. The evaporation occurs at low temperature and low pressure. The condensation occurs at high pressure and high temperature. We can also have transcritical cycles where we don't have any phase change, for instance, in a CO2 heat pump, but we won't consider that in this presentation. So the vapor compression cycle works by a phase change in the condenser and the evaporator, where a high amount of energy is transferred. This phase change depends on pressure, the temperature at which this phase change occurs. We can extract heat at low temperature and reject it at a high temperature. And then we have to take into account that the compressor only uses a small amount of energy to drive the cycle. So we have a high thermal efficiency of the system.